Study magnetic fields, magnetic boundary conditions, series on electromagnetic field theory, lecture number 2.60. When we consider the interface of two different media, the magnetic fields on one side of the interface can be connected to the magnetic fields on the other side. These relations are called magnetic boundary conditions. These are two in number. One gives the relation that exists between tangential components of the magnetic field. The other gives the relation that exists between normal components of the magnetic field. In the present session, we explore these connecting relations or boundary conditions. As already mentioned, magnetic fields on either side to an interface of two different magnetic media can be related. These relations, their origin is Ampere's law and Gauss law for magnetic fields. Here Ampere's law means Ampere's circuital law. Gauss law for magnetic field means closed surface integral B dot dA equal to 0. These relations are already mentioned, called boundary conditions. They are simple and highly useful to find the fields on one side of the interface when fields on the other side of the interface are available. First, let me state the conditions. Tangential component. The statement of condition pertaining to tangential components. The tangential H is continuous across the interface of any two different media except when the interface carries surface currents. When surface current is there over the interface, H is discontinuous. Tangential H is discontinuous by an amount equal to K. Next, move to condition pertaining to normal components. The normal component of B, magnetic flux density, it is continuous across the boundary between any two different media. Either in the presence of current, absence of current, whatever may be the condition over the interface, B is always continuous. That is, normal component of B is always continuous. These are the two boundary conditions pertaining to magnetic fields. How these things come into being, what is the origin, what is the basis. To derive these conditions, we consider an interface. The interface is over XY plane. Below XY plane, medium 2, above XY plane, medium 1. Mu1, M1, Mu2, M2 are permeability and magnetization of the media. So we consider a rectangular loop encompassing the interface partly, lying normal to the XY plane with its shorter side parallel to Z-axis. Notice half of this loop is in medium 1, remaining half is in medium 2. Now we apply Ampere's circuital law over to this loop. That results in boundary condition pertaining to tangential component. To obtain boundary condition pertaining to normal components, we consider a Gaussian pillbox. Half of it above the interface, remaining half below the interface. So half of the box is in medium 1, remaining half in medium 2, as shown in the diagram. Now we apply Gauss law for magnetic fields over this closed surface. Now tangential components. We have considered a rectangular loop in figure A. We apply MMF law. MMF law is this one. Closed line integral H dot dl is J dot dA. This is same as Ampere's circuital law. It is also called MMF law because H dot dl is MMF. E dot dl is EMF. H dot dl is MMF. Now we apply closed line integral. This is closed line integral. So therefore you have to integrate over all the four sides of the rectangle. Bottom side, right side, top side, left side. Now implementing this integration, H by 1 delta y minus Hz2 delta z by 2 minus Hz3 delta z by 2 minus H by 2 delta y plus Hz4 delta z by 2 plus Hz1 delta z by 2 etc Jx delta z delta y. This pertains to this fellow. As you move the longer sides near to each other, shortening the shorter sides, delta z becomes 0. This fellow delta z is there, they become 0. That components become 0, these two components become 0. Ultimately you are left with this one. All these things become 0. Your left side delta H by 1 delta y minus H by 2 delta y. This side you have Jx delta z delta y. Now Jx delta z, it gives surface current density K. Delta y gets cancelled. Jx delta z is surface current. Therefore, you are left with H1 Hy1 minus Hy2 is equal to K. But Hy1 is tangential, parallel to interface. Hy2 is parallel to the interface. Therefore, Ht1 H2 gives you K. We can convert H into, this is basic condition, tangential component condition, magnetic field condition. If you want, we can, it involves field intensity. If you want, you can convert it into flux densities also easily by noting that B equal to mu H. This is the relation. Using this relation, one can convert. Now, to obtain condition on normal components, a pillbox we have to consider. Already it is shown to you, and perform integration. This is Gauss law for magnetic fields. Perform integration. This is closed surface integral. You have to perform integration top face, bottom face, side face, and implementation makes the things like this. Bz1 delta A is the cross sectional area of the Gaussian box. Bz1 delta A minus Bz2 delta A is flux through curved walls. It is equal to 0. As you shrink the height of the Gaussian pillbox, this 5 sides become 0. So Bz1 becomes equal to Bz2, but Z is normal to the interface. So therefore Bn1 equal to Bn2. This is the basic condition. If you want, you can convert it into field intensities also. Sometimes one of the media or both the media, they are magnetic materials. They contain magnetization. In such case, the conditions, tangential condition, normal condition, they can be converted into expressions that involve magnetization. See, Ht1 minus H22 equal to K. Now Ht1 can be written as Bt1 by mu1. Ht2 can be written as Bt2 by mu2 equal to K. And we also know magnetization is equal to Xi m into H. So these two relations, B equal to mu H, magnetization M equal to Xi m H. Using these two relations, one can convert very easily this Ht1, Ht2 into Bt1, Bt2 or Mt2, Mt1. In terms of Mt2, Mt1, we have this kind of relation. So apply with this, with no time, we can get this one. Similarly, normal components also. The condition of normal components also one can convert in terms of field intensities, in terms of magnetizations also. So the connection between magnetizations, it is relevant, connecting tangential component of magnetizations, connecting normal component of magnetizations, boundary conditions in terms of magnetizations. That aspect is relevant when one or both the media are magnetic. There is a law, it's called the refraction law of magnetic flux. Normally refraction, these are associated with light or wave. Here no light, no wave. We are in static fields. Still the law which I am going to introduce, it is called refraction law. Reason is, form wise it appears similar to Snell's law of refraction. That's why it is called refraction law. It involves magnetic flux. That's why it is called refraction law of magnetic flux. Similar to law of refraction in of electric displacement, there is also refraction law for magnetic flux. Let B1 H1 make an angle θ1, B2 H2 make an angle θ2 with a normal to the interface. Here is shown. This is the interface. This is medium 1. This is medium 2. This is B1. This is B2. B1 is making an angle θ1 with the normal. B2 is making an angle θ2 with the normal. Then this law says, we can easily see that tan θ1 by tan θ is mu1 by mu. Mu is permeability. How this relation has come? We have boundary condition on tangential components. We have boundary condition on normal components. Combining these two boundary conditions, within no time one can obtain tan θ1 by tan θ2 equal to mu1 by mu2. This relation, connecting relation, is known as refraction law of magnetic flux. Certain observations can be made. These observations have certain practical importance, so they are being mentioned here. When mu1 is large compared to mu2, the angle θ1 approaches 90, almost regardless of θ2, implying that magnetic flux inside high permeability materials is nearly parallel to the walls and trapped inside, even when the field orientation outside of the medium is nearly perpendicular. Suppose here is highly magnetic material. Flux outside may be like this, but inside it is inside Inside it is perpendicular, parallel to the surface. Flux can escape high mu material best when theta 2 is 90 degrees. This phenomena is critical to the design of motors and other systems incorporating iron or nickel. Flux density B is larger in the medium of larger permeability value. The field intensity H is larger in the medium of smaller permeability. These are certain observations. They carry a lot of practical importance. That's why they are being mentioned here. This is what I want to share as far as magnetic boundary conditions are concerned. To conclude, let me recollect important points. Magnetic boundary conditions connect fields on one side of the interface with the fields on the other side. These are highly useful in finding field on one side when field on the other side is known. These are two in number. One pertains connecting relation between tangential component and other pertains to connection between normal components of the field. This is what I have to share with you. Enough.